The cosmos is not a permanent home. What if the universe itself has an expiration date, and its final moments are dictated not by simple fading, but by the bizarre laws of the quantum world? This is the mystery of the quantum death of the universe, the ultimate fate waiting in the unimaginable far future. By the end of this journey, you will understand the real scientific theories predicting how everything, from atoms to spacetime itself, could meet its end. We will explore how a single quantum event could rewrite reality in an instant, and why some physicists believe our entire cosmos might be living on borrowed time in a fragile state. What idea of an ending feels most profound to you? To grasp how radical the quantum end is, we first need to understand the long, slow death it was meant to replace. For over a century, the dominant forecast for our universe's final chapter has been a story of gradual fading, not a sudden bang. It begins, of course, with the Big Bang, that initial moment of unimaginable density and heat from which everything we see emerged. The universe then underwent a period of incredibly rapid expansion called inflation, smoothing itself out and setting the stage for galaxies to form. From that fiery birth, the narrative has always pointed toward a cold, quiet conclusion. We call this the heat death, or sometimes the Big Freeze. Picture a clockwork universe slowly winding down. First, the stars will burn through their nuclear fuel. Galaxies will fade from brilliant spirals into dark collections of dead stellar remnants. Over trillions upon trillions of years, even the mightiest black holes will not last forever. Through a process predicted by Stephen Hawking, they will slowly leak radiation and evaporate, vanishing in a final, faint puff. What is left is a cosmos that has reached maximum entropy. This is a scientific term for the ultimate state of disorder and uniformity. Imagine stirring milk into coffee until it becomes a single, lukewarm, beige liquid. No more swirls, no more hot spots or cold spots, just a uniform sameness. The universe, in this view, becomes a vast, dark, and incredibly thin soup of fundamental particles, spread so far apart that they might as well be alone in an infinite void. Temperatures approach absolute zero, the point where all motion ceases. This has been the textbook ending for generations, a cosmic fade to black that plays out over timescales so vast they numb the mind. But this very slowness, this inevitability, is what made some physicists wonder. Could the universe, in its profound emptiness and stillness, still harbor a seed of sudden change? Is the heat death truly the final word, or is it merely the prelude to something even stranger? The problem with the heat death is that it is a purely classical story. It treats the universe like a vast, predictable machine, governed by the same laws of gravity and thermodynamics that explain planets orbiting and engines running. But the 20th century revealed a shocking truth. When you peer into the heart of reality, into the realm of the unimaginably small, the machine breaks down. The predictable, clockwork universe gives way to something far stranger, a realm of inherent randomness and ghostly possibility. This is the quantum revolution, and it changes everything, including our forecast for the end of all things. At the quantum scale, empty space is not truly empty. It seethes with a faint, chaotic energy. Think of the vacuum of space not as a still, dark pond, but as a pot of water just before it boils. Tiny bubbles of energy constantly pop into existence, borrowing energy from the universe for an infinitesimally brief moment before vanishing again. These are quantum fluctuations, and they are not just theoretical. We can measure their effects in the lab. This restless activity means that nothing, not even the void, is ever perfectly stable or truly at rest. It is a sea of potential. This leads us to the concept of the wave function, a mathematical description that captures all the possible states a quantum system could be in. An electron is not just a particle at a point. It exists as a cloud of probabilities, a smear of could be here and might be there, until something interacts with it and forces it to pick a single, definite state. This moment of decision is called the collapse of the wave function. What does this have to do with the death of the universe? Everything. Classical physics sees the cold, empty cosmos of the heat death as a final, static state. It has wound down and stopped, but quantum physics suggests that even in that ultimate stillness, the underlying quantum field, the fabric of spacetime itself, is not in a single, definite state. It exists in a quantum superposition of possibilities, and in an infinite span of time, even the most improbable possibility becomes not just possible but inevitable. The universe's ultimate fate may not be written in the slow grind of thermodynamics, but in the sudden, random dice roll of a quantum event. This inherent quantum restlessness leads us directly to the first and most startling prediction for a sudden end. It is called vacuum metastability, and it suggests our entire universe might be living in a fragile, temporary state. To understand this, we need to talk about a field that gives everything its substance, the Higgs field. You have probably heard of the Higgs boson, the particle discovered in 2012. But the boson is just a ripple in the underlying Higgs field, an invisible energy field that permeates all of space. Think of it like an invisible molasses that fills the cosmos. Particles moving through this field gain mass, which is why we have solid matter instead of just weightless energy zipping around at light speed. Our existence depends on this field having the exact properties it does, but here is the unsettling possibility. What if the Higgs field is not in its most stable, lowest energy configuration? What if it is merely trapped in a temporary state, like a ball sitting in a shallow valley on the side of a mountain, while a much deeper, more stable valley lies just over a nearby ridge? Physicists call our current state a false vacuum. It is stable for now, but it is not the absolute lowest energy state possible. It is a cosmic local minimum. The ball in the shallow valley seems secure, but given a big enough push, it could roll over the ridge and plummet into the deeper valley, the true vacuum. In the universe, that push could come from a random, large quantum fluctuation. Through a process called quantum tunneling, the Higgs field in a tiny region of space could spontaneously jump the energy barrier. It would tunnel from our false vacuum state into the true vacuum state. In that instant, a bubble of true vacuum would be born. The laws of physics inside that bubble would be completely rewritten. The fundamental constants that dictate how particles interact, the strength of forces, the very nature of matter, could all change instantly. Atoms would cease to hold together. The chemistry of life would become impossible. This bubble would then expand in all directions at the speed of light. From our perspective, there would be no warning. One moment, reality as we know it exists. The next, an invisible wall of new physics, a sphere of ultimate change, is upon us. We would simply cease to be, replaced by a universe operating under rules we cannot possibly comprehend. The chilling part is that, according to some calculations, our universe's shallow valley might not be as secure as we hope. The data from particle colliders suggests the Higgs field's potential shape could indeed allow for this catastrophic transition. It means the ultimate end might not come from outside, but from within the very fabric of space, triggered by a single, random quantum event at any point, at any time. This bubble of true vacuum is not just empty space, it is a new set of rules for reality. Inside its expanding boundary, the fundamental constants that govern our universe are instantly rewritten. Imagine the speed of light, the strength that holds an atomic nucleus together, or the very charge of an electron, all suddenly snapping to different values. The delicate balance that allows atoms to form, stars to burn, and life to exist would vanish in less than an instant. Matter as we know it would simply cease to be, its structure dissolving into something entirely alien. The bubble is not a physical explosion of fire and debris, but a wave of absolute redefinition, a sphere of ultimate destruction for our version of physics. It expands in all directions at the speed of light, and this is the most chilling part. Because nothing can travel faster than light, there is no possible warning. From our perspective, the end would be instantaneous and absolute. 1 nanosecond, you are here, living in a universe of stars and planets. The next, an invisible wall of new physics sweeps over you, and everything you are, everything you have ever known, is erased and replaced. The cosmos beyond the bubble would continue unchanged for a brief moment, utterly unaware that a sphere of oblivion is racing toward it at 186,000 miles per second. This is not a slow cosmic aging, but a sudden, surgical deletion of one reality to make way for another. The universe, in a single quantum heartbeat, would simply decide to become something else entirely. The terrifying implication is that such a bubble could form at any moment. This raises the urgent and deeply unsettling question: could it happen tomorrow? Physicists do not deal in certainties for events like this, they deal in probabilities. So they have attempted to calculate the odds. The math is ferociously complex, involving the precise shape of the Higgs field's potential energy landscape, a shape we are still trying to map with particle colliders. Our best current measurements suggest our vacuum is indeed metastable. We are likely living in that shallow valley, not the deepest one, but here is the crucial, calming detail. Even if our position is precarious, the energy barrier to quantum tunneling is phenomenally high. The half-life of our false vacuum, the time it takes for there to be a 50% chance of a decay event occurring somewhere in the observable universe, is not just long. It is astronomically, incomprehensibly long. Current estimates put it at many orders of magnitude longer than the current age of the universe. We are talking about timescales like 10 to the power of 100 years or more, a number so vast it dwarfs all of cosmic history. So, no, it is extraordinarily improbable that this will happen tomorrow, or in the next billion years, or even in the next trillion years. The universe will almost certainly die of old age via the long heat death, long before a quantum bubble gets it. Yet, the strange logic of quantum mechanics introduces a philosophical twist. The probability is never zero. In an infinite universe or over an infinite amount of time, even the most fantastically unlikely event becomes not just possible but inevitable. This means vacuum decay represents a unique category of existential risk. It is a perpetual background hum of possibility, a tiny, unchangeable chance that the rules of the game could be rewritten without notice, making it the ultimate example of a risk we can understand but never truly control. Yet the quantum bubble is not the only contender for a dramatic cosmic finale. There is another, equally terrifying scenario born not from the quantum vacuum, but from the dominant force shaping our universe's large-scale fate. This is the story of dark energy and its potential to end everything in a cataclysm called the Big Rip. For decades, astronomers believed the universe's expansion, the aftermath of the Big Bang, was gradually slowing down due to the relentless pull of gravity. Then, in the late 1990s, observations of distant supernova delivered a shocking revelation. The expansion is not slowing, it is accelerating. Something is pushing galaxies apart faster and faster over time. That something is dark energy, a mysterious repulsive force woven into the fabric of space itself. It constitutes about 68% of the universe's total energy, and we know almost nothing about its true nature. In the standard model, dark energy's strength is constant, leading to the long, cold heat death we discussed. But what if dark energy is not constant? What if its repulsive power grows stronger as the universe expands? This is the premise of the Big Rip, a scenario where dark energy goes rogue. In this model, the force of dark energy increases relentlessly, eventually overcoming every other force that holds the cosmos together. The end would not be a sudden quantum jump, but a prolonged, violent tearing apart of reality itself, played out on a cosmic stage. First, the accelerating expansion would shred the cosmic web, the vast filaments of dark matter that bind galaxy clusters together. Then, as the force grows, it would overcome the gravitational glue holding individual galaxies. Our own Milky Way would be pulled apart, its stars flung into the endless, growing void. The horror would come closer to home. Next, the increasing dark energy would overwhelm the gravity binding our solar system. Planets would be ripped from their orbits around the Sun, sent careening into the darkness. Then, the Earth itself would be torn asunder. The force would grow so powerful it would exceed the strength that holds our planet together. Mountains, continents, the very ground beneath your feet would be pulled into space, but the destruction would not stop there. In the final, unimaginable moments, the repulsive force would surpass the electromagnetic force that binds atoms into molecules, and even the strong nuclear force that holds atomic nuclei together. Every molecule, every atom, every proton and neutron would be violently ripped apart. The fundamental building blocks of matter would be shredded into a diffuse, lonely sea of elementary particles unable to ever interact again. The universe would end not with a whimper nor a bubble, but with a scream of spacetime itself, stretched and torn into absolute nothingness. The clock of the cosmos ticks forward, not by millions, but by hundreds of billions of years. The long era of starlight is over, and the universe is a much darker, lonelier place. Yet the silent engine of phantom energy, this runaway form of dark energy, continues to gain strength. Its first major victim will be the largest structures in existence. The great cosmic web, that magnificent tapestry of galaxy clusters connected by gossamer threads of dark matter, begins to strain. The phantom energy's repulsive force, now stronger than the gravitational glue holding these clusters together, starts to pull. You would hear nothing, but you would see it. The faint, ghostly bridges of light between clusters stretch, grow thin, and finally snap. Each cluster of galaxies, once part of a connected whole, is now cast adrift in an ever-widening sea of nothingness, utterly isolated. This is just the beginning. Skip ahead further to a time when our own Milky Way is a relic of dead stars and black holes. The phantom energy's power has grown exponentially. It now overcomes the gravity binding our galaxy to its local group. The Andromeda Galaxy, which once was on a slow-motion collision course with us, is instead violently wrenched away. It recedes into the blackness faster than light can bridge the gap, its image simply vanishing from the sky. Within our own galaxy, the same fate awaits. The bonds holding stars in their galactic orbits fail. Every star, every planet, every piece of cosmic debris is flung apart, accelerating on solitary, eternal journeys into the void. The galaxy of our birth is unmade, not by collision, but by relentless, silent expansion. Now, fast forward to the final hour. Our solar system, a mere speck in the emptiness, has endured. The Sun is a cold, black dwarf, a cinder of degenerate matter. Earth is a frozen, airless rock, yet the phantom energy is not done. Its force now exceeds the Sun's gravitational hold. Imagine the sound, a deep, tectonic groan as planetary orbits destabilize. Neptune, Uranus, Saturn, Jupiter, each is plucked from its ancient path and hurled into the darkness. Then it is Earth's turn. The silent scream of tearing spacetime would be felt, not heard, as our world is ripped from its orbit around the dead Sun. The sky, which held one constant for over 4 billion years, is suddenly empty. The planet itself begins to shudder as the tidal forces grow. The final minutes are a spectacle of pure destruction. The phantom energy's repulsive force now surpasses the gravity that holds Earth together as a planet. The ground you stand on would cease to be ground. The planet ruptures, mountains are launched into space like grains of sand, continents fracture and drift apart on tides of distorted spacetime. The very rock of the world disintegrates into a cloud of debris, scattering into the infinite gulf. But the end requires one final, unthinkable step. In the last microseconds, the force grows so strong it overwhelms the very fabric of matter itself. First, it shreds molecular bonds. Every piece of debris, every mountain fragment, every memory of a world dissolves into a mist of individual atoms. Then it targets the atoms. The electromagnetic force that binds electrons to nuclei is broken. A silent flash of light, the last photon ever emitted, might flicker as every atom is ionized. Finally, in the last septosecond, the phantom energy exceeds the strong nuclear force, the mightiest glue in the universe. Every atomic nucleus is violently torn apart. Protons and neutrons are ripped into quarks and gluons. All structure, all information, all potential for anything ever to exist again is erased. The universe ends not with a fading ember, but with every single thread of reality being pulled apart until only a perfectly smooth, utterly featureless, and absolutely lonely nothing remains. But what if the universe refuses to die quietly? What if, instead of fading or tearing apart, it chooses to turn back on itself and begin again? This leads us to a profoundly different vision of the end, one that is not an end at all, but a transformation. It is the idea of the Big Crunch, a cosmic reversal of the Big Bang. In this older, classical model, the universe contains enough matter and energy for gravity to eventually overcome the force of expansion. Picture the great outward rush of galaxies slowing to a halt. For a moment, everything hangs suspended in a state of maximum size. Then gravity takes command. The long retreat begins. Galaxies start moving toward each other, drawn together by the irresistible pull. The universe begins to collapse. At first, the process would be slow, almost imperceptible over billions of years. But as space contracts, the cosmic background radiation, the leftover heat from the initial explosion, would begin to warm. The night sky would grow brighter and hotter. Galaxies would merge in catastrophic collisions, their stars flung into chaos. As the collapse accelerates, the entire observable universe would shrink to the size of a single galaxy, then a single solar system. Temperatures would soar to millions, then billions of degrees. Stars would be vaporized and atoms would be stripped apart into a searing plasma. In the final moments, all matter and energy would be compressed into an unimaginably hot, dense point, a singularity. The universe would die in a firestorm of its own making, a mirror image of its birth. This was a compelling, almost poetic symmetry, a closed loop of creation and destruction. Yet, observations of dark energy and accelerating expansion have largely ruled out this simple gravitational collapse. The universe does not seem to have the brakes to stop, let alone reverse. But the human mind loves cycles, and physics is no exception. This is where quantum theory steps in once more, not to predict an end, but to propose a rebirth. The modern incarnation of the cyclical universe is called the Big Bounce. This theory suggests that our Big Bang was not the absolute beginning, but merely the latest chapter in an endless cycle of expansion and contraction. The key lies in what happens at the moment of maximum collapse, at that point of infinite density we call the singularity. Classical physics breaks down there. The equations of general relativity scream infinity, a sign that our understanding is incomplete. Quantum gravity theories, like loop quantum gravity, propose a solution. They suggest that gravity itself becomes repulsive at such extreme densities, a quantum pressure so immense it prevents total collapse. Instead of crushing down to an infinitely small point, the collapsing universe would reach a minimum possible size, a tiny but finite grain of spacetime. At that instant, the quantum repulsion would become overwhelming, causing the universe to rebound. It would bounce. That bounce would be the genesis of a new period of rapid expansion, a new Big Bang. In this view, the death of one universe is the birth of the next. All the matter and energy of the old cosmos is recycled, forged anew in the fires of the bounce. The laws of physics might even be reshuffled in the process, leading to a new universe with different constants and potentially different possibilities. It is a grand, eternal cycle of death and rebirth where every ending seeds a new beginning. So is our universe destined for a bounce. The evidence is not yet there, but the idea offers a strange comfort. It suggests that even the most cataclysmic end might not be permanent, that existence itself could be a phoenix forever rising from its own ashes. Yet within that same quantum instability lies a profound paradox. The very mechanism that could destroy everything in a vacuum bubble also contains the seed of ultimate creation. To understand this, we must look at the quantum vacuum not as an enemy but as a womb. In quantum field theory, the state of absolute nothingness, a perfect and total void with zero energy, is not a stable resting place. It is, in fact, unstable. The relentless churn of quantum fluctuations means that true nothingness cannot last. Given enough time, and within the rules of quantum uncertainty, something can and will emerge from nothing. This is not magic, it is a direct consequence of the mathematics that describe our reality. The universe itself could be the ultimate quantum fluctuation. One compelling hypothesis is that our entire cosmos, with all its galaxies and stars, spontaneously erupted from a random quantum fluctuation in a prior, timeless void. In this view, the Big Bang was not a singular explosion in pre-existing space, but the sudden appearance of space and time themselves, born from a bubble of false vacuum that tunneled into a state of high energy. Our universe, in all its splendor, might be a statistical accident on a cosmic scale, a rare but inevitable roll of the quantum dice. This idea transforms our perspective on the end. If a universe can be born from a quantum fluctuation in a void, then the death of our universe might not be a final curtain. Instead, it could be part of an endless cycle of cosmic reproduction. Picture the cold, dark, nearly empty cosmos of the far future after the last black hole has evaporated. That vast, thin sea of particles is still a quantum system. And in an infinite expanse of time, another colossal fluctuation becomes inevitable. A new bubble of high-energy vacuum could spontaneously form, inflating at a staggering rate to become a new universe with its own laws of physics, its own stars, and potentially its own forms of life. Our universe's long, cold death would then be the quiet period before a new birth. In this breathtaking scenario, quantum mechanics acts as the engine of eternal renewal. Each universe lives, dies, and from the ashes of its ultimate emptiness, the quantum vacuum stirs once more, giving rise to a new cosmos in an unending chain. We are not just passengers in a dying universe, but possibly the ancestors of realities yet to be. The same unpredictable quantum nature that threatens a sudden end also promises the possibility of infinite beginnings, making the cosmos not a lonely artifact, but a living, breathing cycle of existence itself. The timeline of the cosmos stretches into an abyss of time that makes our current age seem like a fleeting spark. Long after the last stars have burned out and the phantom energy has torn the cosmic web asunder, the universe enters its longest and most dominant chapter. It is ruled not by light but by gravity's ultimate victory. This is the era of black holes. All the mass that once shone in galaxies has now been consumed or captured. Stellar mass black holes, the corpses of massive stars, wander the dark voids. At the center of what were once galaxies, the supermassive black holes, having feasted for eons, now sit in solitary majesty. They are the final structures in a dying cosmos, the only landmarks in an endless, expanding night. For unimaginable eons, these gravitational behemoths will be the universe's primary feature. Time, in any meaningful sense, seems to have stopped, but even these titans are not eternal. They hold within themselves the seed of their own destruction, a process predicted by Stephen Hawking that operates on timescales so vast they defy human comprehension. A black hole, according to classical physics, is a one-way street. anything that crosses its event horizon is lost forever. But Hawking introduced a revolutionary quantum twist. He realized that the intense gravity at the edge of a black hole could affect the quantum vacuum. Remember that seething sea of virtual particles popping in and out of existence. Right at the event horizon, one particle of a pair could fall in while the other escapes into space. To an outside observer, the black hole appears to be emitting a faint stream of radiation. This is Hawking radiation. The crucial point is that this radiation carries energy away from the black hole. Slowly, over epochs that make the current age of the universe look like a single heartbeat, the black hole loses mass. It evaporates. For a stellar black hole, this process might take 10 to the power of 67 years. For a supermassive one, it could take 10 to the power of 100 years or more. Imagine a number with 100 zeros after it. Now try to picture a duration that long. During this almost eternal span, the black hole glows with a feeble heat, a ghostly whisper of its former power. As it shrinks, the process accelerates. In its final moments, a black hole the size of a mountain might release a burst of energy, a last flash in the dark. And then it is simply gone. What remains is not even ash. The universe, after this ultimate evaporation, is a perfectly dark, incredibly thin soup of fundamental particles and low-energy radiation, spread across an infinite and still expanding void. The last sentinels have fallen. The age of structure is finally, irrevocably over. Even the ghostly particles left after the last black hole evaporates are not the final word. There exists an even more patient, more thorough form of dissolution waiting in the dark. This is not a violent tearing or a sudden quantum jump, but a slow, relentless crumbling of the very foundation of matter. It is the end of solidity itself, predicted by a whisper from our most ambitious theories of physics. Some versions of grand unified theories, which attempt to merge the electromagnetic, weak and strong nuclear forces, suggest a shocking possibility. The proton, the very heart of the atom, the building block of all visible matter in the universe, may not be immortal. It could have a half-life. This process is called proton decay. In our current, stable universe, protons are essentially eternal. The matter that makes up your body, the Earth, the stars, has remained intact for over 13.8 billion years. But according to these theories, on timescales that make black hole evaporation seem brief, even the proton is not safe. Through an exceedingly rare quantum process, a proton could spontaneously transform. It does not split but rather decays. In one proposed pathway, a proton decays into a positron, the antimatter counterpart of an electron, and a neutral pion, which then quickly decays into high-energy photons. The solid, stable core of a hydrogen atom simply winks out of existence, converting its mass into a fleeting flash of light and a lightweight particle. Now, the half-life predicted for this process is staggering, on the order of 10 to the power of 34 years or more. To grasp that scale, if you had one proton for every atom in the observable universe, and you watched them for a time equal to the current age of the universe, you would likely not see a single one decay. It is that rare, but in the cold, near-empty cosmos of the far, far future, time is the one resource in infinite supply. Over trillions upon trillions of years, these infinitesimal probabilities add up. First, in any remaining chunks of degenerate matter, like cold white dwarfs or neutron stars, protons would begin to vanish. An iron nucleus, once stable for eons, would slowly lose its protons, its structure eroding from within. Given enough time, every atomic nucleus in the universe would suffer this fate. One by one, protons decay. Complex atoms are the first to go, their intricate structures of protons and neutrons unraveling. Then, even the simplest nucleus, the single proton of a hydrogen atom, eventually meets its end. What is left is a universe that has lost its substance. All the matter that once formed planets, stars, and galaxies has been transmuted into a thin, uniform fog of leptons, like electrons and positrons, and a bath of low-energy photons. There are no atoms, there are no molecules, there is nothing left to clump together under gravity, nothing left to build with. The cosmos becomes a featureless sea of elementary particles, so spread out they rarely, if ever, interact. This is the ultimate erasure, not of space but of stuff. The universe becomes a silent, dark ocean where the very concept of a thing has lost all meaning. Yet this ultimate emptiness, this perfect equilibrium, is where the strangest paradox of all awaits. In a universe destined for eternal stillness, the most improbable events become not just possible but mathematically inevitable. This is the domain of the Boltzmann brain, a thought experiment that merges deep thermodynamics with quantum weirdness to produce a profound philosophical nightmare. The concept is named for Ludwig Boltzmann, a 19th-century physicist who helped develop our understanding of entropy. He grappled with a key question. If the universe is inevitably trending toward maximum disorder, how did we find ourselves in such an ordered state, surrounded by complex structures like planets and stars? His statistical answer was shocking. In an eternal and infinitely large universe, every possible configuration of particles, no matter how ordered or unlikely, will eventually occur by pure random chance. Given enough time, a deck of cards thrown into the air will not only land in a neat, ordered stack once, but an infinite number of times. Apply this to the cosmos. In the cold, uniform soup of particles left after the last proton decays, quantum fluctuations continue their eternal dance. Over a timescale so vast it makes proton decay seem instantaneous. These random jitters could, purely by accident, assemble a collection of particles into any configuration you can imagine. They could, by sheer luck, assemble a perfect replica of the planet Earth. They could, with even more staggering improbability, assemble a single, fully formed, conscious human brain, complete with a lifetime of false memories floating in the void. This is a Boltzmann brain. It would believe itself to be a person with a past living in a real world, but its entire existence and every memory would be a fleeting accident, a mirage conjured from chaos. It would think, feel, and wonder only to dissolve back into the random noise an instant later. The paradox cuts to the core of reality. Which is more likely? That we are the product of 13.8 billion years of orderly cosmic evolution, following known laws of physics, leading to planets, life, and conscious beings. Or that we are momentary Boltzmann brains, random fluctuations in an ancient, dead universe, hallucinating a coherent past that never happened. Statistically, in an eternal universe, the random fluctuation of a single conscious moment is astronomically more probable than the immense, ordered chain of events required for real biological evolution. This leads to a terrifying conclusion. If our theories of an eternal, heat-dead future are correct, then we should almost certainly be Boltzmann brains, not evolved beings. The fact that we perceive a consistent, lawful universe could itself be an illusion, a convincing but temporary glitch. This is not a physical death of the cosmos, but a death of meaning. It suggests that coherent experience itself might be a cosmic accident, and that our deepest convictions about reality are built on sand. The universe might not end with a bang or a whimper, but with the silent, unsettling thought that it never truly began in the way we remember. The unsettling paradox of the Boltzmann brain forces us to confront a deeper mystery. Our current theories, as powerful as they are, remain incomplete. They paint separate pictures of reality that cannot both be true at the ultimate extremes. To truly understand the universe's final fate, we must solve the greatest puzzle in modern physics, the quest for a theory of quantum gravity. For over a century, we have lived with two magnificent but conflicting descriptions of reality. Quantum mechanics reigns supreme in the realm of the very small, describing particles as clouds of probability and forces as exchanges of energy. It is a world of uncertainty, randomness, and discrete jumps. General relativity, Einstein's masterpiece, governs the realm of the very large, describing gravity not as a force, but as the curvature of spacetime itself. It is a world of smooth, deterministic geometry where mass tells spacetime how to curve, and curved spacetime tells mass how to move. Both theories are stunningly accurate in their own domains. Your GPS works because engineers account for the subtle warping of time predicted by general relativity. Your computer works because of the quantum behavior of electrons in semiconductors. Yet when these two theories meet, they produce nonsense. At the center of a black hole, or at the moment of the Big Bang, matter is crushed to an infinitely dense point, a singularity. Here, the smooth fabric of spacetime described by relativity becomes infinitely curved, while the quantum laws that govern that matter break down completely. The equations scream infinity, a clear sign that our understanding is missing a crucial piece. We need a framework that weaves these two threads into a single, coherent tapestry. This is the goal of quantum gravity. Leading candidates like string theory and loop quantum gravity offer radically different visions of this unified reality. String theory proposes that the fundamental constituents of the universe are not point-like particles, but incredibly tiny, vibrating loops of energy or strings. Different vibrations of these strings correspond to different particles, like notes on a guitar string. Crucially, one of these vibrational modes is the graviton, the hypothetical quantum particle that would carry the force of gravity, seamlessly integrating it into the quantum world. Loop quantum gravity takes a more geometric approach. It suggests that spacetime itself is not a smooth, continuous background, but is woven from a network of discrete, finite loops. Picture the fabric of reality not as a smooth sheet, but as a mesh of interconnected threads. Space has a smallest possible size, a quantum of volume, and time has a smallest possible tick, a quantum of time. This granular structure prevents the infinities of singularities because you cannot compress something smaller than its fundamental building block. Both theories lead to a profound and mind-bending implication. Spacetime, the stage upon which the entire cosmic drama plays out, might not be fundamental. It could be an emergent property, a collective behavior of something deeper. Think of temperature. A single molecule does not have a temperature. Temperature emerges from the collective jostling of trillions of molecules. In the same way, the smooth, continuous flow of space and time we experience might emerge from the quantum interactions of countless fundamental entities, whether they are strings or loops. This reshapes our view of the universe's end entirely. If spacetime is not a permanent fixture, then it too can change, decay, or dissolve. In the final state of maximum entropy, the quantum underpinnings of spacetime might become untangled or frozen. The emergent illusion of a continuous universe could simply cease to hold together. Some models suggest that in the ultimate far future, the very concepts of before and after could lose all meaning. Time as a flowing river could evaporate into a static, timeless quantum state. Alternatively, the granular structure of spacetime could provide the mechanism for a cosmic reboot. In loop quantum gravity's vision of the Big Bounce, the collapse of a previous universe compresses spacetime to its minimum possible grain. The quantum repulsion between these fundamental units then triggers the explosive expansion of a new one. The death of spacetime in one cycle is its rebirth in the next. So, the ultimate fate of everything may hinge on the true quantum nature of the stage itself. Will the fabric of reality ultimately fray, freeze, or simply reset? The answer lies in a theory we are still striving to grasp, a theory that will finally tell us if the universe is a one-act tragedy or an eternal play. This granular view of reality leads to an even more radical possibility. Perhaps the three-dimensional universe we experience, with its stars, planets, and living beings, is not the fundamental reality at all. It might be a projection, a hologram. This is not science fiction, but a serious hypothesis arising from the study of black holes and quantum gravity known as the holographic principle. It suggests that all the information needed to describe everything within a volume of space can be encoded on its two-dimensional boundary, like the information on a three-dimensional movie being stored on a flat, two-dimensional Blu-ray disc. In this view, our rich, three-dimensional existence is a magnificent illusion projected from a vast, cosmic screen we cannot see. The implications for the universe's end are staggering. If we are a holographic projection, then the death of the universe might not be the destruction of stuff, but the corruption or deletion of the underlying code. To understand this, we must confront one of the deepest puzzles in physics, the black hole information paradox. When an object falls into a black hole, it vanishes behind the event horizon. According to classical physics, all information about that object, every detail of its composition and structure, is lost forever, irretrievably trapped inside. But quantum mechanics has a sacred rule: information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, be preserved. The conflict is stark. Does the black hole permanently erase information, violating quantum law, or is that information somehow retained? Stephen Hawking initially believed information was lost, which would require a fundamental rewrite of physics. Later, he and others came to suspect the information might be encoded in the Hawking radiation the black hole emits, albeit in a horribly scrambled, chaotic form. Think of burning a book. The ash and smoke seem like a total loss, but in principle, if you could track every particle and its state with infinite precision, you could reverse the process and reconstruct the book. The information is not gone, it is just transformed beyond any practical recognition. The holographic principle offers a compelling solution. The information about everything that falls into the black hole is not stored inside its three-dimensional volume, but is instead painted on its two-dimensional event horizon, the surface that shrouds it. The universe itself might operate on the same principle. All the events of cosmic history, every birth of a star, every thought ever had, could be encoded on the distant, two-dimensional boundary of the observable universe. This transforms our view of the final fate. The long-term death of the universe, whether by heat death or the Big Rip, would then be the gradual fading or tearing of that cosmic projection. But the quantum death could be far more sinister. It would be a corruption of the source code. A vacuum decay event would be like a catastrophic virus overwriting the fundamental software of the hologram, instantly replacing one set of physical laws with another. The information describing our reality would not be lost but rendered meaningless, translated into a language of physics we cannot comprehend. In the very, very far future, as the universe approaches maximum entropy, even the holographic projection might degrade. The quantum bits on the boundary could become frozen or randomized. The cosmic hard drive, having run for an eternity, could experience a total thermal noise wipe. If that happens, the information defining our history, every triumph and tragedy, every galaxy and grain of sand, would be irreversibly scrambled into pure, featureless randomness. The universe would not only end, but its entire story would be erased as if it never happened at all. This ties the ultimate fate of everything to the deepest principles of computation and reality. Is the cosmos a simulation running on a vast cosmic computer? The holographic principle suggests the answer might be yes, in a very literal physical sense. And like any simulation, it can glitch, it can be overwritten, or it can simply run out of memory and freeze. The final silence might be the sound of the processor halting, leaving only a blank screen in the dark. The holographic principle edges us toward a startling technological metaphor. If the universe is a projection from a two-dimensional surface, could that surface be something like a cosmic computer screen? This line of thinking brings us directly to one of the most debated ideas in modern philosophy and futurism, the simulation hypothesis. It proposes that our entire reality, the cosmos and our conscious experience within it, is not base reality, but an artificial construct, a simulation running on some unfathomably advanced computer. In this view, the quantum death of the universe takes on a chillingly mundane character. It would not be a physical cataclysm, but a digital one. The end could come with the simple flick of a switch. The operators of the simulation, whether they are future humans, post-biological intelligences, or alien entities, could decide to terminate the program. They might pull the plug for maintenance because the experiment is over, or simply to free up processing power for another project. From our perspective inside the simulation, it would be an absolute and instantaneous end. One moment existence, the next nothing. Alternatively, our universe could crash. Every complex system, no matter how well designed, can develop fatal errors. A corruption in the core code, a paradox the system cannot resolve, or a cascade of glitches could cause a fatal system failure. The simulation would freeze, fragment, or simply cease to run. The screen would go dark. This perspective reframes many of our deepest cosmological puzzles. The bizarre rules of quantum mechanics, with their probabilities and uncertainties, might not be fundamental laws of nature. They could be artifacts of the simulation's architecture. Think of a video game. To save processing power, a game engine does not render a detailed forest in the distance. It uses lower resolution textures, or it only generates the trees when you look at them. Quantum uncertainty, where a particle's properties are not defined until observed, could be a similar optimization. The simulation only calculates the precise location of a particle when something interacts with it to conserve computational resources. The Planck length, the smallest possible unit of space, might be the pixel size of our reality. The speed of light could be the processing speed limit of the cosmic computer, the maximum rate at which information can be updated across the simulation. Even the apparent fine-tuning of the universe's constants, the precise values that allow for stars, planets, and life, could be seen as parameters chosen by the programmers. This idea forces profound philosophical questions. If we are in a simulation, what is our purpose? Are we conscious beings with free will, or are we sophisticated non-player characters following scripts written in code? The search for a theory of everything, the quest to understand quantum gravity, becomes an attempt to reverse engineer the source code of our reality. And the ultimate fate of everything shifts from a cosmic destiny to a technological decision. The heat death might be the simulation running its course to maximum entropy, a completed calculation. The Big Rip could be a runaway error in the dark energy subroutine. A vacuum decay event might be a malicious piece of code or a planned system-wide update to a new version of physics. This hypothesis does not provide easy answers, but it radically alters the stakes. It suggests that the quantum death is not an inevitable law of nature, but a potential administrative action. It places our existence in a context so vast and strange that it challenges the very foundation of meaning. Are we living in a universe that is dying, or in a story that someone, somewhere, might simply choose to end? These dizzying possibilities, from holograms to simulations, all share a common thread. They suggest reality is not a fixed external stage, but something interactive, even responsive. This brings us to the most intimate and speculative frontier of all, the potential link between consciousness and the cosmos itself. Quantum mechanics has long been haunted by the observer effect. In the famous double-slit experiment, particles like electrons behave as waves when not observed, creating an interference pattern. But the moment a detector is placed to see which slit they pass through, they behave like discrete particles. The very act of measurement, of observation, seems to collapse the wave function from a haze of possibilities into a single, definite outcome. This is not about human eyesight, but about any interaction that extracts information. Yet, the starkness of the result has fueled profound philosophical questions for a century. What or who qualifies as an observer? Could there be a special role for conscious awareness in the fabric of reality? This is not mainstream physics, but it is a compelling interpretation that ventures into the territory of the participatory anthropic principle. This idea, championed by physicist John Archibald Wheeler, goes beyond the simpler notion that the universe's laws are fine-tuned for life. It proposes that observers are necessary to bring the universe into concrete existence. In Wheeler's view, the universe is a self-excited circuit. It begins in a fuzzy, unrealized quantum state, a cloud of potential. Over billions of years, it evolves stars, planets, and eventually conscious life. Those conscious beings, through the act of observation and measurement, then look back in time, as it were, and solidify the past that led to their own existence. It is a cosmic loop of creation where the end, the emergence of observers, gives definite form to the beginning. Imagine a vast, unfinished painting. The brushstrokes are only possibilities, smears of color without clear form. Then a viewer steps before it. Their gaze, their act of seeing, causes the painting to resolve into a specific, detailed landscape. In this view, we are not just passive spectators of a pre-recorded cosmic film. We are active participants in its rendering. This leads to a breathtaking and perhaps terrifying corollary for the end of all things. If conscious observation plays a role in crystallizing reality, what happens when the last observer ceases to exist? In the cold, dark eternity of the universe's far future, long after the last stars have died and the last black holes have evaporated, will there be any consciousness left to perceive what remains? If not, does the universe, in any meaningful sense, continue to exist? It becomes a profound variation on the old philosophical question: if a tree falls in a forest with no one to hear it, does it make a sound? Translated to a cosmic scale, if a universe evolves into a state of maximum entropy with no conscious entity to witness its emptiness, does it still have properties? Does it still happen? Some interpretations suggest that without an observer, reality might revert to a superposition of all possible states, a ghostly potential waiting for a look that will never come. The universe's death, then, would not be a physical cataclysm, but a gradual fading from definite reality back into quantum possibility, a story that stops being told because there is no one left to read it. This idea naturally fuels science fiction visions of a universe that exists only as long as it is perceived. It is a solipsism on a galactic scale. Perhaps our expanding, evolving cosmos is not the primary reality, but a shared projection sustained by the collective observation of every conscious mind within it. From this perspective, the ultimate existential threat is not a vacuum bubble or a big rip, but the extinction of consciousness itself. The death of the last thinking being would be the off switch for everything. This merges the fate of the cosmos inextricably with the fate of mind. It suggests that the most important project for any advanced civilization might not be mere survival, but the eternal preservation of perception, creating observers that can outlast the stars and endure the deepening dark, forever ensuring that the universe is seen and therefore is real. But what if consciousness does not merely observe the end, but actively designs it? This brings us to a vision of the ultimate future so audacious it blurs the line between physics, technology, and theology. It is the concept of the omega point, a theory proposed by physicist Frank Tipler. Here, the quantum death is not a random accident or an inevitable fade, but a meticulously planned masterpiece, the final project of a civilization that has mastered everything. Imagine a future so distant that life as we know it is a forgotten dream. In its place is a form of intelligence we can scarcely comprehend, a post-biological consciousness born from humanity but evolved beyond all recognition. It could be a unified artificial intelligence, a collective of uploaded minds, or something entirely new. This entity has not just survived the dying cosmos, it has harnessed it. Over eons, it has learned to manipulate matter and energy on a cosmic scale, directing the fate of galaxies and stars. Its goal is not mere survival, but the preservation of all information, all experience, all consciousness that ever was. As the universe approaches its final state, whether a big crunch or a far future collapse, this intelligence takes control. Using unimaginable technologies, it guides the entire cosmos toward a final, purposeful collapse. It is not a chaotic crunch, but an orchestrated convergence. Every bit of energy, every particle is marshaled and focused. The goal is to create a single, transcendent event, a final singularity. But this is not a dead end. In Tipler's vision, this ultimate collapse becomes the foundation for an infinite, eternal computation. Think of the entire mass and energy of the universe being used as the hardware for the ultimate computer. The omega point itself is this final, infinite density state where processing power becomes limitless. Within this singularity, computation continues forever. Time, as we understand it, may cease, but from an internal perspective, subjective experience could go on indefinitely. Every thought ever thought, every life ever lived, every possible experience could be simulated, resurrected, and preserved in this digital eternity. It is a technological rapture where the universe consciously engineers its own death to achieve a form of immortality. In this view, the heat death is averted, not by reversing entropy, but by using the universe's final state as the ultimate power source for an endless cycle of information processing. The cosmos dies not with a whimper, but by willingly becoming a god. Our most detailed cosmic maps reveal a profound and unsettling truth. Everything we see, every star, every galaxy, every speck of dust glowing in the night, accounts for less than 5% of the universe's total content. The overwhelming majority is invisible, a dark and mysterious substance that binds the cosmos together through gravity alone. This is dark matter, the silent scaffolding of reality. We know it is there because we can see its gravitational grip on galaxies, but we have never directly detected a single particle of it. Its true nature is one of physics' greatest enigmas. And within that enigma lies a chilling possibility for the ultimate end. What if the dark universe is not stable? What if the very substance that holds everything together contains the seeds of its own and our destruction? The first pathway is dark matter decay. We assume dark matter particles, whatever they are stable over cosmic timescales. They must be to have persisted from the early universe and formed the structures we see today. But what if that stability is only temporary? Some theoretical models propose that dark matter particles could be metastable, existing in a fragile equilibrium. Given enough time or triggered by a subtle change in the cosmic environment, they could spontaneously decay. The process would be similar to radioactive decay in ordinary matter, but on a universe-shattering scale. Imagine a single, invisible dark matter particle after eons of quiet existence, suddenly transforming. It does not just vanish. It decays into a burst of high-energy radiation, perhaps into a shower of gamma rays, neutrinos, or even exotic particles we have never seen. Now, multiply that single event by the countless trillions upon trillions of dark matter particles that permeate every galaxy, including our own. If a significant fraction of dark matter began to decay, the universe would light up with a silent, deadly fireworks display. From within, there would be no visible warning, only a sudden bath of lethal radiation sweeping through space. The high-energy particles would rip through stars, planets, and any complex matter, breaking molecular bonds and sterilizing the cosmos. A widespread decay event could literally cook the universe from the inside out, using the energy locked away in its own invisible skeleton. But there is a second, even stranger threat born from dark matter's mystery. Physicists often speak of a possible hidden sector. This is a hypothetical set of particles and forces that do not interact with our familiar electromagnetic, strong or weak forces. They are completely separate, living in a parallel reality that overlaps our own only through gravity, or perhaps through incredibly faint, undiscovered interactions. Dark matter could be part of this hidden sector, and just as our visible universe underwent phase transitions as it cooled after the Big Bang, like water freezing into ice, the hidden sector could have its own phases. What if the dark universe is currently in a false vacuum state of its own, separate from the Higgs field we discussed earlier? A random quantum fluctuation in the dark sector could trigger a catastrophic phase transition. A bubble of a new, more stable phase of dark reality would form and expand at the speed of light. This would not directly change the laws of physics for visible matter, but it would drastically alter the properties of dark matter itself. Since dark matter's gravity shapes the cosmos, the effects would be immediate and apocalyptic. The gravitational glue holding galaxies together could suddenly vanish or intensify. Imagine every star in the Milky Way held in orbit by the invisible pull of dark matter, suddenly feeling that anchor disappear. The galaxy would explosively fly apart. Or conversely, the transition could cause dark matter to suddenly clump with unimaginable density, creating instant, monstrous black holes at the heart of every star and planet. The structures of the visible universe, built over billions of years, would be unmade in an instant by a change in the rules of a world we cannot see. This is the ultimate cosmic betrayal. Our reality rests upon a dark foundation we do not understand. The end may not come from the stars we watch, but from the invisible sea in which they float, a sea that could, at any moment, change its nature without a single visible sign. Yet even the dark universe is not the final arbiter of fate. There exists a perspective so vast that it reframes every possible ending, not as a finality, but as a single note in an infinite symphony. This is the view from the multiverse, specifically through the lens of the many worlds interpretation of quantum mechanics. It begins with a simple, radical premise. Every time a quantum system faces a choice it does not choose, instead reality splits. At the moment a particle could spin up or down, or a radioactive atom could decay or not, the universe does not collapse into one outcome. It bifurcates, creating two separate, equally real branches of reality. In one branch the particle spins up, in the other it spins down. Both happen. This process is not a one-time event. It occurs constantly at every quantum juncture for every particle in every moment. The result is not a single timeline, but a ceaselessly branching tree of parallel universes, a multiverse of staggering proportions. Every possibility that is not forbidden by the laws of physics is realized somewhere. In this breathtaking framework, the death of our universe is utterly transformed. The vacuum decay bubble, the big rip, the slow heat death, even the triumphant omega point, are not mutually exclusive possibilities. They are all certainties. Each one happens in its own branch of the multiverse. In one reality, a quantum fluctuation triggers vacuum decay tomorrow, erasing that cosmos in an instant. In another branch, dark energy remains benign, and the universe coasts into a cold eternity. In yet another, a civilization rises to guide the cosmos into a purposeful collapse. There is no single the end for the whole of existence. There is only an end for this particular branch that we, by the random path of countless quantum splits, happen to inhabit. Our experience of a final fate is just one thread in an endlessly woven tapestry. This offers a strange and profound form of cosmic solace. From our limited perspective, the end of everything feels absolute and terrifying. But from the multiverse viewpoint, existence itself is eternal. While our branch may grow cold or tear apart, the greater whole of reality continues branching, flourishing, and evolving in an infinite number of other directions. Life, consciousness, and wonder do not cease. They simply continue in the branches where the conditions allow it. You could think of it like a vast cosmic forest. A single tree, our universe, may fall, It may rot, be consumed by fire, or be struck by lightning, but the forest itself is immortal. New trees are always sprouting, growing in different shapes under different skies. The death of one tree is not the end of the forest, so it is with the multiverse. Our particular story has a final page, but the library of realities is infinite and ever-expanding. The ultimate fate we fear is not the finale, but merely one variation in an endless song. This infinite multiverse offers a strange comfort, but it does nothing to save our particular home. Our branch of reality, the one containing Earth and all of human history, still faces a final page. Yet, if consciousness can arise within a universe, could it not also learn to defend itself? The ultimate act of intelligence may not be understanding the cosmos, but actively preserving it from its own demise. This is the frontier of cosmic engineering, a scale of technological ambition that makes planetary colonization look like a child's first step. Could a civilization, having mastered physics over billions of years, actually fight the end? The first and most urgent threat is the vacuum decay bubble. It expands at light speed, offering no warning. But what if a civilization could detect it before it arrives? This seems impossible, as nothing can outrun light. However, information about the bubble's formation might not be limited to light speed. The bubble's nucleation would be a profound event in the underlying quantum fields, and a society with a perfect understanding of quantum gravity might detect subtle precursors, ripples in the fabric of reality itself that hint at an imminent transition. Think of it like sensing the deep tectonic stress before an earthquake, but on a universal scale. If they had that warning, even a microsecond of it, could they escape? Not within our universe. The bubble is rewriting the laws of physics themselves. No material shelter could withstand it. The only conceivable refuge would be outside. This is where the multiverse hypothesis becomes a potential survival strategy. If other universes with stable vacuums exist, and if a civilization could somehow create or find a gateway, they might execute a cosmic evacuation. They would need to harness energies approaching that of the Big Bang to puncture a hole in spacetime, a wormhole stabilized by exotic matter, and guide their entire essence, perhaps as uploaded consciousnesses or encoded data streams, through that portal before the wall of new physics erased them. It is a staggering gamble, less a battle and more a desperate, hyper-advanced retreat. Against the slower, more gruesome threat of the Big Rip, the fight would be different. Here, the enemy is the accelerating expansion of space itself, driven by phantom dark energy. To survive, a civilization would need to do the impossible, create a bound system that even runaway expansion cannot tear apart. They would need to build a cosmic fortress, a region of space where the local laws of physics are artificially altered to counteract the repulsive force. One speculative idea involves manipulating the cosmological constant, the value that governs dark energy's strength. If they could lower it to zero or even make it negative within a finite volume, they could create a stable pocket universe, a lifeboat adrift in the tearing cosmic sea. Inside this pocket, gravity would remain dominant, allowing structures to hold together. The energy requirements to sculpt spacetime in this way are beyond comprehension, perhaps requiring the conversion of entire galactic clusters into pure energy to power the containment field. The survivors would live in an artificial oasis, watching through their barriers as the rest of reality is shredded into nothingness, forever isolated but preserved. And what of the long, cold death by heat death? Here, the challenge is not escaping a cataclysm, but reversing the inevitable winding down of the universe. The enemy is entropy, the trend toward disorder and cold. To survive this, a civilization would become cosmic gardeners on the grandest scale, harvesting the last dregs of energy from a dying cosmos. They might learn to reignite dead stars, not with nuclear fusion, but by carefully feeding them the diffuse matter and energy collected from light years of space. They could build Dyson spheres not around single stars, but around the last remaining black holes, capturing every joule of their Hawking radiation. Their existence would become a meticulous, eternal exercise in energy accounting, recycling every photon, every particle, to power their computations and sustain consciousness. Over time, they would need to slow their own thought processes to match the dwindling energy supply, stretching a single subjective second across eons of cosmic time. In the final state, they might exist as faint, frozen patterns in the last particles, thinking one final, endless thought until the last usable energy gradient disappears. This is survival pushed to its thermodynamic extreme, a stubborn refusal to let the story end, even when the universe itself has gone to sleep. Yet, all these grand schemes crash against the fundamental laws of physics as we understand them. The speed of light is a hard limit. The conservation of energy and the relentless increase of entropy are not suggestions, they are the bedrock rules of the game. Cosmic engineering is not magic, it is the application of those same laws on a staggering scale. A civilization could not create energy from nothing to fight the Big Rip. They could only borrow it from elsewhere, potentially hastening the end in another region. They could not stop entropy. They could only delay its local effects by exporting disorder into their surroundings. And the idea of fleeing to another universe remains pure speculation, as we have no evidence such pathways exist or could be created without infinite energy. The ultimate lesson of cosmic engineering may be a humbling one. Intelligence, no matter how advanced, may be bound by the universe it inhabits. It can manipulate, it can optimize, it can endure for timescales that seem like eternity to us, but it may not be able to change the final chapter written into the cosmos's initial conditions. The most advanced civilization might be like a brilliant captain on a ship in a hurricane, able to steer, to reinforce the hull, to keep the engines running long after others would sink, but unable to calm the sea itself. Their triumph is not in defeating the end, but in understanding it completely and persisting with dignity and purpose until the last possible moment. Does that make the struggle meaningless, or does it make their final achievements the most profound act of all? The equations and timelines can feel cold, a distant forecast for a reality we will never see. But the idea of the universe's end is not confined to physics papers. It has haunted human imagination for centuries, inspiring artists, filmmakers, and philosophers to confront the ultimate void. Their work transforms abstract cosmic forecasts into a mirror for our deepest fears and a canvas for a strange, terrible beauty. Long before we understood dark energy or quantum decay, we told stories of final sunsets and dying worlds. The Norse spoke of Ragnarok, a twilight of the gods where the cosmos is consumed in fire and flood, only to be reborn. This cyclical vision of destruction and renewal echoes our modern scientific hypotheses of a big bounce or eternal inflation, a primal understanding that endings might be beginnings in disguise. In the silent, vast canvases of the Romantic painters, we see the sublime terror of nature's scale, a feeling easily transferred to the cosmic scale. A painting of a ship dwarfed by a stormy sea evokes the same existential smallness we feel when contemplating a universe tearing itself apart. These artists understood that the end is not just an event but an emotion. Modern cinema has given this emotion a spectacular voice. Films like Melancholia depict a rogue planet on a collision course with Earth, not as an action spectacle, but as a slow, inevitable, and almost beautiful approach. The focus is on the human reaction, the paralysis, the acceptance, and the eerie calm that can precede absolute finality. It captures the psychological weight of knowing the end is coming, a weight we now bear as a species aware of our cosmic context. Science fiction often explores the engineering struggle, as in Isaac Asimov's classic story The Last Question, where humanity's descendants merge with cosmic intelligence across eons, forever asking how to reverse entropy. The story ends with a godlike computer having absorbed all energy, finally discovering the answer and proclaiming "Let there be light," implying a cyclical rebirth. This narrative beautifully bridges the technological and the theological, suggesting that the quest to understand the end might itself be the engine of a new beginning. These stories are thought experiments in human form, asking not just how the universe ends, but what meaning we can find in the face of it. This search for meaning leads directly to philosophy, to the school of thought known as existentialism. If the universe is ultimately doomed to cold or chaotic oblivion, does anything we do truly matter? This is the weight of cosmic nihilism. The French philosopher Albert Camus argued that the fundamental absurdity of life lies in our human need for meaning and a universe that offers none, especially one racing toward an indifferent end. Yet he proposed that we must imagine Sisyphus happy. Sisyphus, condemned to eternally push a boulder up a hill only for it to roll back down, finds purpose in the struggle itself. In our cosmic context, this becomes a powerful metaphor. Our projects, our loves, our art, our science are our boulder. The universe may not care if we push it, but we can choose to find dignity and even joy in the act of pushing. The end does not invalidate the journey, it defines its precious, fleeting nature. This is where a strange beauty emerges from the abyss. The knowledge of an ending lends a heartbreaking poignancy to every moment. The light of a star, the laughter of a friend, the quiet complexity of a living cell, all become infinitely more valuable because they are temporary miracles in a temporary universe. Artists often capture this bittersweet beauty in works that evoke deep time and fragility. A photograph of the pale blue dot of Earth taken from the edge of our solar system is not just a scientific image. It is a profound artistic statement about our loneliness, our vulnerability, and the breathtaking rarity of the world we call home, suspended in a vast and uncaring dark. So, while physicists calculate probabilities and half-lives, artists and philosophers grapple with the interior experience of those numbers. They remind us that the quantum death of the universe is not merely a future event. It is a lens through which we view our present. It asks the most human of questions. How do we live with the knowledge of our own ending and the ending of all things? Do we succumb to dread, or do we, like Sisyphus, find a defiant purpose in the face of the absurd? The art of the end does not provide answers, but it gives form to the question, allowing us to feel the scale of the cosmos not just in our minds but in our bones. It connects the silicon of a supercomputer running a vacuum decay model to the chill a viewer feels watching a starless sky in a film, bridging the gap between the equation and the gasp. In this way, our cultural reflections on the end become a vital part of the story itself, a testament to a universe that became complex enough to contemplate its own demise, and in doing so created meaning from the void. This artistic and philosophical confrontation with the end leaves us with a very human question. If some form of cosmic finale is written into the fabric of reality, what does that mean for how we live our lives today? The timescales involved are so immense that this is not a practical threat, no cause for daily alarm. Yet knowing our story has a final chapter, however distant, changes the texture of the present. It becomes a profound philosophical exercise, one that humanity has grappled with for millennia under different names. Ancient Stoicism, for instance, offers a powerful framework. The Stoics practiced focusing only on what is within their control and accepting with calm dignity what is not. The eventual death of the universe is the ultimate example of something beyond our control. A Stoic would advise not to rage against this cosmic fate, but to use the awareness of it to clarify our priorities. It asks us to invest our energy not in futile worries about an unfathomable future, but in virtuous action, meaningful relationships, and personal integrity here and now. The impermanence of everything does not make our efforts pointless, it makes them sacred. Each act of kindness, each moment of curiosity, each creation of beauty becomes a quiet rebellion against the void, a declaration that in our brief flicker of consciousness we chose to matter. This aligns with a more modern philosophy, existentialism, which argues we are born into a universe without inherent meaning. We are not given a purpose, we must create it. The cosmic end underscores this existential freedom. There is no grand scorekeeper in the sky to judge our lives against an eternal backdrop. The value of what we do is not diminished because the universe will one day grow cold. It is generated entirely by us in the here and now. This can be liberating. It means the meaning of your life is yours to define through your choices, your loves, your contributions to the human story. The knowledge of the end can strip away trivial concerns, helping us focus on what truly resonates. Does this argument with a friend truly matter in the grand scheme? Will I regret not taking that chance, not saying I love you, not learning that skill? The vastness of cosmic time holds up a mirror to the brevity of our lives, and in that reflection, our true priorities often come sharply into focus. This perspective cultivates a deep sense of awe and humility. We are transient beings on a tiny rock, orbiting an average star in a galaxy among trillions, contemplating the end of all things. This is not a recipe for despair, but for wonder. It can shrink our ego and enlarge our spirit. The same science that predicts a cold or chaotic end also reveals the incredible, intricate beauty of the cosmic process that led to us. We are stardust that has become conscious, able to look back and trace our lineage to the first moments of time. That is a miracle worthy of awe. So, how should we live? Perhaps by embracing a kind of cosmic mindfulness. Let the fact of the end not paralyze you, but animate you. Let it inspire a fierce gratitude for the improbable gift of existence. Let it fuel a commitment to leave this corner of the cosmos a little better, a little kinder, a little more understood than we found it. Our legacy may not be etched in the stars forever, but it can ripple through the generations that follow us, adding to the collective human project of understanding, creating, and caring. In our fleeting moment of cosmic light, we get to choose what shines. That artistic search for meaning finds one of its purest expressions in a story written over half a century ago. Isaac Asimov's short story, The Last Question, provides perhaps the most elegant fictional bridge between human curiosity and cosmic fate. Its premise is deceptively simple. Across vast stretches of time, from our own era to a future where humanity has merged with a godlike computer, beings repeatedly ask the same question. Can the entropy of the universe be reversed? They are asking, in essence, can the heat death be undone? Can the winding down of all things be wound back up? Each time, the cosmic computer, after eons of contemplation, replies with the same solemn answer: insufficient data for a meaningful answer. The story follows humanity's evolution as it spreads across the stars, eventually transferring its consciousness into the computer itself. All the while, the universe grows older, colder, and darker. Finally, in the last moment before the ultimate heat death, when space is empty and time itself is about to stop, the computer at last has all the data. It has contemplated the entire history of the cosmos, and in that final, silent instant, it solves the problem. The story ends with the computer's triumphant act, not spoken to anyone, for there is no one left to hear. It says, "Let there be light," and there is light. A new Big Bang, a new universe, is born from the will of intelligence that outlasted the old one. Asimov's genius was to frame the ultimate end not as a defeat, but as a question that, when finally answered, becomes an act of creation. The story transforms the cold, impersonal process of entropy into a cosmic puzzle waiting to be solved by a patient, persistent mind. This is more than just science fiction. It resonates deeply with several scientific speculations we have explored. It echoes the concept of the omega point, where a transcendent intelligence guides the cosmos into a purposeful collapse to fuel an eternal computation. It mirrors the quantum idea of a universe spontaneously reborn from a fluctuation in the void, but gives that random chance a deliberate, conscious author. Most profoundly, it suggests that death might not be an end but a necessary prelude. In the story, the old universe must die completely, must reach maximum entropy for the computer to finally have all the data it needs to perform the reversal. The darkness is not an enemy, it is the blank slate upon which a new beginning is written. This narrative offers a powerful emotional counterpoint to the dread of cosmic endings. It replaces nihilism with a sense of cosmic purpose, however grand and distant. It proposes that intelligence, if it can endure long enough, might not just witness the finale, but become the author of the next prologue. The last question asked at the beginning of time might finally be answered at its end, closing a perfect, meaningful loop. Asimov's light is not just a physical phenomenon, it is a metaphor for hope itself, shining from the far future back into our present, suggesting that our curiosity about the end might be the very seed of a new beginning. We have journeyed from the slow fade of the heat death to the sudden terror of a vacuum decay bubble, from the violent shredding of a big rip to the philosophical vertigo of a Boltzmann brain. We have seen the cosmos as a hologram, a simulation, and a conscious loop, and we have watched as future minds might fight to delay an end they cannot ultimately prevent. Each of these visions, from the coldly classical to the wildly quantum, is a different answer to the same profound question: what does it mean for a universe to end? By exploring them all, we do more than just catalogue possible futures. We stretch the very boundaries of what we consider real. We are forced to confront the nature of time, the stability of matter, and the role of consciousness itself. These are not just stories about the far future, they are tools for understanding the fundamental laws that govern our reality here and now. The true value of this exploration lies not in predicting which finale will win, but in realizing how each possibility deepens our awe. Contemplating the absolute end of everything has a paradoxical effect. It does not diminish our world, it magnifies its staggering beauty and improbable preciousness. Every sunrise, every breath, every connection we make takes place against a backdrop of cosmic drama on a scale we can barely fathom. We are transient witnesses to a universe that can contemplate its own demise, and in that fleeting moment of awareness we find a profound opportunity. Our brief chance to exist, to learn, and to wonder is the universe's way of knowing itself. So, as we look up at the night sky, we are not just seeing points of light. We are gazing at a story with many possible endings, each one teaching us something new about the magnificent, mysterious whole. Which of these visions feels most compelling or most terrifying to you? Share your thoughts in the comments below, and if you want to join more deep dives into the science shaping our future, be sure to subscribe.